Welcome to 5 Minute Papers on AI for the Planet. I'm Grace Lindsay. Our paper today is Sustain DC, Benchmarking for Sustainable Data Center Control. Data centers are the buildings where the cloud is stored. They contain racks upon racks of servers that perform the computational work of running the internet, and therefore they require a lot of energy to operate. With the rise of large AI models being used everywhere, energy demand from data centers is skyrocketing. And with that comes an increase in pollution from greenhouse gas emissions. But this raises an interesting question. Can we use methods from AI and machine learning to reduce emissions from data centers? In this paper, the authors introduce a computational environment to allow researchers to explore exactly that question. The class of algorithms most useful for optimizing data center performance are reinforcement learning algorithms, which train an agent to take actions in an environment to receive reward. This paper focuses on a particular subclass known as multi-agent reinforcement learning, or MARL. In MARL, multiple agents are trained to work together in a shared environment. One tricky aspect about training RL agents, however, is that you need an interactive environment where the agents can try out actions and learn from the outcomes. Of course, we can't hand over the keys to a real data center when training these agents, so this paper provides a realistic simulation of a data center. The simulated data center has all of the parts and processes that might matter for modeling energy use and emissions. Just like real servers running computational jobs, the simulated servers produce heat, which rises to the ceiling and is drafted out to cooling towers through a multi-stage HVAC system. This system is simulated according to the equations of thermofluid dynamics. The amount of cooling needed will depend on current weather at the data center location, which is also provided in this simulation. This weather data comes from locations with high concentrations of data centers in the US. Each of the stages of the HVAC system, along with the servers themselves, require energy to run. That energy is provided by a simulated energy grid. Importantly, a given amount of energy produced by the grid will not always produce the same amount of greenhouse gas emissions. This is because at different times of day, energy producers use different mixes of energy sources, from emission-free sources like solar to emissions-heavy sources like burning coal. To be able to minimize emissions, this simulation provides the data center a measure of the grid carbon intensity over time, which is based on real energy production data from states that house data centers. The data center is also equipped with batteries that allow it to pull energy from the grid when carbon intensity is low and store it for later use. All of these data center components have configurable parameters that allow users to mimic a range of real-world scenarios. Finally, the data center is provided with workloads, which represent the computational jobs the customers want to run on the servers. These jobs will be labeled as delayable, meaning they can be put off and run at a time where compute demand or carbon intensity is lower, or non-delayable. The statistics for these workloads also come from real demand patterns observed by companies like Google and Alibaba. In total, the goal of the RL agents is to find a way to satisfy all the customer demand while producing the fewest emissions possible. So let's see how they do. This paper tests MARL methods using up to 3 different agents, one to control job load scheduling, one to control the cooling system, and one to control battery charging and discharging. These agents get rewards by minimizing the monthly carbon footprint while still running submitted jobs on time. The reward functions can also include terms that penalize outcomes such as high operational costs or water usage. The authors show that using these trained agents, particularly the agent tasked with controlling the cooling system, can reduce greenhouse gas emissions. Here, approaches that include the cooling system agent achieve a roughly 9% emissions reduction compared to those that don't. The authors also explore how the reward structure impacts performance. In a MARL setting, you can let all the agents learn from the same reward, or you can give each agent individual rewards that are tailored to its role. Here, the authors find that a moderate amount of sharing of reward information across the agents allows them to better balance performance on all of the evaluation metrics. Finally, the authors make a really important observation about how these methods work across different data centers. Here, different colors represent different methods used to train the agents. As you can see, the pattern of performance of these methods differs substantially for data centers simulated to be in different locations. This means that a method that works well in one setting won't be the best performer in another. This lack of generalization also suggests that it's really important that the simulation be a good replica of the real data center. Otherwise, the agents trained in simulation won't work well in the real world. Luckily, the point of creating the simulated data center environment is to give researchers the chance to make these methods better and more robust. So we may be able to see progress in tackling the important problem of data center emissions. That's all for this episode. Make sure to subscribe to this channel for more examples of how AI can be used to protect our planet.